Okay, so next are the critical properties. And all they come from is just setting that Mach equal to 1. So I would just take the relationships before, but then just set it equal to 1. Now you have this relationship here. Or now my other reference that I'm talking about with respect to stagnation are these properties here. All I've been doing is just subbed in Mach equal 1. Nothing fancy at all. Right, so these are evaluated because I can relate stagnation to critical. Okay, so usually this critical and then subscript naught is a stagnation. Sometimes I've seen subscript C for critical, but usually I see a subscript star for these critical properties. All right. Well, then there's nothing more than just dividing then out the stagnation to get relationships that relate T anything to T critical, or quantity to critical, right? So if you do that and just take the relationships before, again, you'll get this terrible relationship. So I'm just going to I'll call like a large pi group, let's say. Okay. Defining this pi group as this other quantity that we have right here, you'll get then that the ratio of the temperatures. So now it's referring to the critical reference, and then same things. This is critical as well. That would be a critical Mach number for the critical Mach number, and it has a critical speed of sound. Right, so then that's right. This is sort of a beastly thing to calculate, and they write it off in detail for every of those equations, but it just gets unruly. So just to think of this as just some quantity I calculate based on my medium and my velocity, and then I get these relationships for reference pressures, reference temperatures, and reference densities. So all good and fun. But maybe some words then on like how on earth do you use these things, or why would I even use them in the first place? So it really sort of this idea of like for the stagnation ones, you could have something like this, right? Some reservoir where inside, the Mach is 0 on the inside. There's some pressure, and then there's some temperature here. And you're looking then at exit conditions, right? And it can be any combination of not knowing the Mach, not knowing the pressure, not knowing the temperature, but you have to set those equations. If you can set some of these states, right? So if this is state B and this is state A, those first stagnation relationships can let you evaluate the next state, previously or before, right? We're here, P naught, T naught. So these are stagnation pressures and stagnation temperatures, which can be calculated or tabulated. So if you look up in graphs, you can figure out what these values are, calculate things, and you can get these pressures or temperatures on the outside, or the velocity on the outside as well. Calculating the velocity is a little tricky because this is how nasty that expression is, but you could, right? You've related state A to state B, stagnation state to exit state. So this is sort of the chamber of gas that's releasing all of its flow, etc. And then we have the situation of what is the velocity there. Is the Mach number greater than 1 or less than 1? These are things that you can figure out based on those relationships. The critical Mach number pictures that you draw are these, is these diverging nozzle, maybe converging nozzle things, right? Where here now you set that Mach equals 1 at the throat. So now I have references to, right, here's state A, and then I can even have state B back here, or B can be back here, right? So I go from here to the Mach 1, or from Mach 1 to the Mach B. Those relationships now tell you how to get from state A to state B. And even here, there's even something called a critical area right here that helps you size the duct. So those next equation, the second critical parameters, what they do is they help size ducts for saying, I need Mach to be 1 at the throat. So so what's the cross-sectional area I need to achieve that? Right? So those second equations are usually for sizing throats. So stagnation is a release problem, and then these throat problems are usually sizing a throat. Okay, and then right back here you can have a Mach of something, a pressure here, and then a temperature here. Or likewise here, you could not know the Mach here, could not know the pressure here, you could not know the temperature here, right? But some combination, could not know all three at the same time, because that's not how equations work, right? You have to have one equation, one unknown, but that's how you would use them, right? You would set the states of A and set the states of B. If you don't know one of the states, you can use the equations, okay? Okay, so then it's really just sort of to compare incompressible flow to compressible flow problems, right? What do we do? What do we do every time, right? So, right, the question of the incompressible flow we always want is to get liquid from A to B, right? So if you're getting liquid from A to B, usually this entire class what we did is we derived expressions to sub into Bernoulli's equations, like the friction factors or more like things like that, right? So then you use your energy equation, solve for state A or start with B. So then you can use right? So then you use Bernoulli's to solve for unknowns in state A or state B, or if you know state A and state B, maybe solve for something involved in the Bernoulli equation. But that was it, right? So then in compressible flow, what are we doing, right? So compressible flow, we're doing state A to state B of a gas or a compressible liquid or a compressible fluid, right? Compressible flow, right? I said it was process dependent, so it would also be like, in my compressible process, get fluid from A to B. But with a liquid, it's just so incredibly hard to achieve those values. So usually gas dynamics is what we say. But it's the same goal. I'm going to get gas from state A to state B. This is the undergrad version of these types of problems, because in the undergraduate version, you go into the actual velocity distributions for these types of problems. Okay? And then, so then state 2, instead of using Bernoulli's equation to solve these things, you use, right, just use fancier. Right, fancy relationships, i.e. the isentropic flows. You can use the Fano relations. Or use Rayleigh lines. I haven't gone over these two, so I haven't done that. No, we've really done those. So it's the same process we've gone through, right? We did a bunch of work on using the continuity and the momentum equation to sub into energy somehow to get from gas from A to B, and now you have state A and state B, and you have to set things, and you can solve for them that way. And you just appreciate how somewhat simple all this stuff is. It's just wrapped up in a bunch of nasty equations. Now we can comment a little more now on actual like flow rate, right? In incompressible, we use volumetric flow rate because the density was constant, right? But for compressible flow, we need to use an actual mass flow rate, right? Right? Because this can change. Right? So that's the whole point. We're going to talk about this mass flow rate for a bit. Because this is how you would derive critical areas. Or throat. Okay, so the mass flow rate, I need to talk about that because densities can change. So, right, m dot is a rho, a, and then a velocity. And now we're going to do more and more substitutions. So rho, let's go ideal gas on that. Involve temperature in there. Here's A. And now I'm going to do a dirty trick where I'm going to multiply by C over C. Just multiplying by 1. Okay. That would make this V over C times a C. Now this is a Mach number. Always, 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 you want things to be in terms of Mach numbers. You'll see why when we talk about supersonic, subsonic. That's weird. And then this is, okay. So see, this is ideal gas law, ideal gas law. Okay, more substitutions and you get the mass flow rate is equal to an area, a Mach number, pressure, so right now I just have a mass flow rate in terms of a Mach number, pressures, and then ratios of temperatures. All right. So goal now is to turn these into ratios. Right? So yes. Okay, yeah, so what we do here, Mach, yeah, it's the same dirty trick. All right, so, right, you sub in by, you multiply it through by another bunch of ones, right? Because, I'm sorry, right, you're doing the same thing where you multiply by a bunch of ones to get those stagnation reference points. So I had a pressure here, so that's the same as pressure times P naught over P naught. And then I have this. And then this is over T. Right? Just multiplying by one of these two things because now I can, right? Now I can use those stagnation relationships to sub in for here and get more Mach information now because I have these ratios. I know what these ratios are based on Mach and properties of the gas from the equations I already have. And these are really nasty equations, so I'll just write, I need to probably use the whole chalkboard for something. That's okay. So just, again, now you're just going to sub in those relationships you had. Okay, and then this is a fraction. So maybe, right, this is a Mach divided by this whole thing raised to a power. There's your area, and then there's terms over here. And then here's what's impressive now. A critical mass flow can be calculated now by inserting 1 for Mach. So the whole purpose of doing this now is getting this critical Mach number. And this is surprising just because of, you'll see, this is interesting. Okay. And then some critical area. So this is telling you that, right, there's a critical area, and all this stuff is only referring to the fluid property and the stagnation property of. So from going from 0 to anything, there's just a critical Mach number that exists, and that gives you this critical area to get to Mach 1. You're limited by that, and that's the big takeaway, right? Now you can take that and you can get an area ratio. Here's your critical area ratio. Effectively, I got rid of the mass flow rate term and just looked at area to make this equation. All right. So now, reference area to this critical area is governed by this. And there's a maximum mass flow rate to be achieved. You can't beat that. And that is the idea that you get from this. And I'll just draw pictures of the next round to really go over converging and diverging nozzles and to see how this theory can help you maybe rationalize what's happening with the pressures and the mass flow rates occurring in those types of systems for isentropic flows.